We are done, people. Okay, so let's not complicate this any more than this has to be. Here we go. So it's lecture 21. And that is Monday, the 11th of May. So here we go. This is what I wanted to do today. So the idea is that infinite sum, which is your series. Now you can write functions as series. You can write, I'm going to stress any as series. The question is twofold. How do we do it and why do we do it? So here is the how part. So I'm just going to start with the how of it. It is going to be, so how do we do it? I'm going to say we start one box. We start with x to the n equals 0 to infinity, 1 over 1 minus x. We use three techniques, A, I, D. Can you tell me what are those so that we understand those notes when you read them later? So what are these AID? And you can type it in or you can unmute and say. Very good. Algebra, integral, and the D is actually, there we go, derivative. So what happens here? Oh, these two, R stays the same. And these are the notes I would make to myself. Oh, if I take a different, if I take a derivative, I lose one term, because the constant term just goes to 0 after I take the derivative. And for algebra, I'm just going to replace x by something and compute the radius. So that is the idea. The other idea is I'm going to use the definition. And what do I mean by definition? Oh, I'm going to use this to write it as Taylor series, which we're going to do today, right away, which is n equals 0 to infinity Cn x minus a to the n, where what is a? Oh, a is the center. And as Maclaurin series, which is summation n equals 0 to infinity Cn x to the n, where the center is at 0. The question is, in both of these, what are Cn's? Oh, Cn is the nth derivative at the center over n factorial. So I used the table to do this. So how did the table go, people? Did you have a chance to look at it? How did the table go? So I'm going to wait for your comments here. I'm going to just say it's going to be the nth derivative of f at the center divided by n factorial. That is where the table comes in. I'm also going to say, notice that this coefficient, this Cn, is multiplied by x minus a to the n or x to the n. So in both the cases, the table serves very, very well. So any comments about the table? The table was all right. So no comments about the table? The table, I just want to know, does the table work or does it not work? And thank you, Trent. So here we go. So then the question is, in this block, how do I find the R and the I? Oh, use the ratio test. So first I'm going to deal with the how part, and then I'm going to deal with the why part. So let's just start. So here is my first example. If I have time today, then I'm going to show you one example that can be done both ways. It's used to pick, and that's the problem of plenty that I kept talking about. It's not that you have no way of doing it, you have multiple ways of doing it. So you are going to be savvy about this one and pick the one that works the best. But here it is. Let's take the first example. And first I'm going to take the simple one. So f of x is 2 to the x And I want to write this as Maclaurin series. So here is how I start. So solution. I know I want to write this 2 to the x as summation n equals 0 to infinity Cn x to the n. Why x to the n? Because Maclaurin series is Taylor series centered at 0. So I just start my table. And to find the R and I, I'm going to use the ratio test. So let's just start. So here is the table. So here is n. Here is the nth derivative. And I'm going to start writing in. So this is the nth derivative of f at 0. Why? Because the center is 0. So I keep everything ready. And the last one is my Cnth. Not only that, I do want to say to you that I use this n in this way, that this is x to the 0, this is x to the 1, because this is x squared, this is x cubed, and everything is ready. I just have to compute and go from there. So ready for this one then? Or you're still writing? Because I want you with me on this one. Are we ready there?
Yeah, I'm ready.
Thank you, Russell. So here we go. So.
Oh, Cicely's still writing.
Okay. Thank you for that as well, Russell. Because I would have easily missed that. So I'm going to wait for a minute. Cicely, let me know when all of you are there. Because this is the thing. You practice with me right now is exactly what you said, Russell. You've got this couple of questions with you because you have practiced it. It's all about being very methodical. The other part, since you're writing, I want to say this. Why do we have to be methodical? You start taking shortcuts. Do not take shortcuts. Why do you think machines can do this? Machines can do this because they need very, very minutely broken down, very logical steps. There is a method to it. You go from 1 to 2. You don't go from 1 to 3. 1, 2, 3, and that is how methodical you have to be. You have to be almost like machines. If you want to talk to them, then have a discipline sort of like them. Having said that, here we go. So n equals 0. So start this one for me. So are we taking any derivative here? So this is going to be what? Just the function 2 to the x. So what is 2 to the 0?
That'd be 1.
Thank you. So now we are taking the first derivative. So what is the first derivative of this one?
I always get confused by these. It's what? X?
So it is 2 to the x ln of 2. You're forgetting, William, that this is not x squared. This is a variable. To use the formula that you used, this has to be a constant. X to the n, the derivative is n x to the n minus 1, where n is a constant. And that's why I said I picked this example exactly for that reason. So what do you get here? 2 to the 0 ln 2, which is what? ln 2 over 1 factorial. And now I start drawing lines because from here it all becomes. So we move on. We are taking the second derivative now. So the second derivative of this one will be what? And I'm going to say this. Notice how I'm writing it now. So I'm going to say this ln of 2, which was a constant, 2 to the x ln 2. I'm just going to change my arrow and I'm going to say this is the derivative. This ln 2 was the leftover. So I'm going to write, oh, this is 2 to the 0 ln 2 squared. So this seems to be ln 2 squared over 2 factorial. I'm going to move my x cubed down here, but see, if you do the work, then you have the series in front of you. So the third derivative, again, I'm going to write it These two are constants, so I'm going to write them ln2 squared. The derivative of this one is 2 to the x ln2. And so I get 2 to the 0 ln2 cubed. And this is ln2 cubed over 3 factorial x cubed. And I think we should do one more and then we should get the idea. So the fourth derivative, and that is the one I want from you. So what would be the fourth derivative?
Well,
go on.
If the pattern holds, ln2 cubed 2x ln2.
Thank you, sir. It's not so bad, really. And so this is 2 to the 0, ln2 to the fourth, ln2 to the fourth over 4 factorial x to the fourth. If you write it the way I'm writing it, then there it is. You have your power series. You're building it up. I'm just going to say, okay, so 2 to the x seems to be 1 plus ln2 over 1 factorial x, ln2 squared over 2 factorial x squared, ln2 cubed over 3 factorial x cubed, and so on and so forth. And then, as you said, Russell, the right word, the pattern. So now what am I doing? I'm just writing it in notation. So I want to write 2 to the x. You're going to tell me summation n equals what to what. And what should I be writing here?
I think it's n equals 1 to infinity.
But then what about this one, Russell? Because if n equals 1, it seems you're starting here. Because you have 1 factorial, 2 factorial, 3 factorial. Why don't we start from 0 to infinity? And then I want you to break it down this way. At least I look at it this way. First, the easiest one, the powers of x, which are going to be what? X to the n? Then I'm going to look at ln2. And as you rightly pointed out, if the pattern holds, then it seems like ln2 to the n over n factorial. And that's about it, isn't it? This is it. This is the series. Because n equals 0 is this, n equals 1 is this, n equals 2 is this, n equals 3 is this, and so on and so forth. You want to find the ratio, so the radius of convergence. Let's use the ratio test, which is going to be n approaches infinity, ln2 to the n plus 1, x to the n plus 1, n plus 1 factorial, n factorial, ln2 to the n, x to the n. We have done this enough number of times, so I'm just going to say limit as n approaches infinity. If you work the way I work, then you know what I do. I just gather all of them together. I'm not writing it now because you've seen this enough number of times. And this is going to be 1 over n plus 1. And I'm going to pause. So far, so good. No questions there?
Not yet.
Very good. So I'm just going to say, we'll remember limit of product, product of limits. So I know that limit as n approaches infinity of this one is just ln2. This one is just going to be absolute value of x. I'm interested in the third one. What about this one? This one is going to be
0.
Thank you, sir. Which is what? When you multiply, no matter what numbers you multiply with 0, it's always going to be less than 1, isn't it? So, by ratio test, what happens? This one converges for all values of x. Where was the center again? 0. You're saying this is always, the limit is always less than 1, because it's always going to be 0, no matter what value of x you put in there. And so there you go, r is infinity. And that's the brilliant part about it. So what are you saying? You are saying that this works for any x. And so now think like your calculator. So you ask your calculator to do 2 to the 1.5. It's not going to multiply. It goes even basic than that. It adds. Addition is much more simpler operation than multiplication. So however your powerful machine is, the more terms it adds, the more, what to say, the better estimation that you have for 2 to the 1.5. Does that make sense? And that's the value of it. It's for any x. You can put anything you want there. What about 2 to the 225? Go for it. But remember, your machine should be able to handle these large sums, because it will be 225 to the 0 plus 225 to the 1, and so on and so forth. Are we ready for the next example? So this was Maclaurin. I want to take Taylor series now. Any questions about this one? So I'm going to pause, let you catch up, but you're going to let me know if you're ready for the next one. Because we do have to do some of these. We haven't done Taylor series yet. So you're going to give us green lights when you're ready. The rest of you, you're silent. I'm going to assume that's a good silence. In other words, there are no questions there. Okay, so here we go. So example 2 then. So this is of a Taylor series. What is a Taylor series? Remember, the center is not 0. Center is A, where A is not 0. I'm just going to say if A is 0, it's Maclaurin. That's it. That's the difference. So I want to take this example first, that f of x equals cosine x. I want to write this as a series, and A is pi. So the center is pi. So first understand what that means. It means you're writing f of x, which is equal to cosine x, which is summation n equals 0 to infinity, Cn x minus pi to the n. What is Cn? That doesn't change. I'm just keeping it writing because I want to keep it in the play. What is Cn again? Oh, it's the nth derivative. D is for derivative of. And if you want, customize this. You can write it pertaining to a problem. So I'm going to say it's the nth derivative of cosine x at pi over n factorial. So you can ready it the way you want it to be. And I'm going to start with the table. So here we go. So this is going to be n. This is going to be the nth d. This is going to be the nth d at pi. This is going to be Cn. And this is how I like to start. So I'm just going to say, oh, this is going to be x minus a to the 0, x minus a to the 1, and so on and so forth. And what am I saying by that? This is how I make it ready. So this is 0. This is 1. So this is x minus a to the 1, and so on and so forth. So start this one for me. So tell me, 0 derivative. So we're not taking any derivative. So it is what? Cosine of x. So what is cosine of pi? And remember, you're a calculator, so don't worry about all that. So cosine of pi is, thank you, Lucas, -1. So the first derivative That means what? You make your table the way you want it to look like. So cosine of x, the derivative is going to be negative sine x. So I'm going to go sine of pi or negative sine of pi, which is 0. So I'm going to fill in this table till maybe 4, not more, once I see the pattern, as Russell pointed out. So we are going to go the derivative of this one, which is going to be negative cosine of x. So that's negative cosine of pi, which is 1. And this is x minus, I should say pi here, x minus pi squared. So I'm going to go one more.
Oh, it's just going to be 0 and then back to negative.
There we go, sir. So this is going to be sine x, sine of pi, which is 0. Now we go to 4. So this is going to be what? Cosine of x. And we hit that. We are going to start back here again. And this is cosine of pi. And this is negative 1. And this is x minus pi to the 4th. So again, this is it. This is that series. This is that Taylor series. I have just found some members of it, but that's the thing. I just wanted to see a pattern there. And so we are just going to say that this one is going to be cosine of x. I'm just going to write that. This is negative 1. If you want, you can write x minus pi to the 0 plus 1. Oh, we forgot to write this one, isn't it? This is 2 factorial. So I'm going to throw in there 2 factorial x minus pi squared. See, we wrote it here. This is over 4 factorial. So negative 1 over 4 factorial x minus pi to the 4th. And an infinite series there. So what is the first thing we observe? It's an alternating series. Why? And I'm going to write it carefully here. So it is cosine x, which is negative 1, plus 1 over 2 factorial x minus pi squared, minus 1 over 4 factorial x minus pi to the 4th. I can assure you, because we go all the way back, this is going to be negative 1 over 6 factorial, right? Because the fifth one is going to be sine x, so it's going to be 6 factorial x minus pi to the 6th, and so on and so forth. Now we just have to write it in notation. So this is going to be cosine of x, summation. Remember, here is a trick. Whenever this is there, then probably it is n equals 0 term. So I'm going to write n equals 0 to infinity. And I'm going to let you take care of, I already know this is x minus pi to the n, is it? So I'm going to let you fill this. And so tell me what I should be writing here. Over what factorial? So any idea? You're absolutely right. You're absolutely right, Cecily. So any idea how this one will go?
I mean, I don't think it's in factorial because half of the factorials disappear.
Very good. But then who remains, Russell? We don't care about the disappear. They're all evens, isn't it?
Right.
And so I can write this as what? If it is an even number. What does an even number mean? They are all multiples of 2. There we go. So it is 2n factorial. The exponent would be 2n because these are the same. So once you figure out this, this is figured out, or whichever way. And then what happens? This is an alternating series. So if this is an alternating series, remember your n equals 0 term, you want it to be negative. Your n equals 2 term, you want it to be positive, and so on and so forth. So this is going to be what? Negative 1 to the 2n, can we say that? Or n plus 1? I don't know which one works. So I'm just going to throw in there, how about n plus 1? And my apologies, this is not n equals 2, this is n equals 1. Why is that n equals 1? Because you wrote it as 2n factorial. Are we okay now? And I'm going to build on this one. So I want to pause here and I want to say if there are any questions, I want to know them now. So take your time if you're writing, go through all of it.
So the zero terms, they're a push, like they're not important to the final series?
Oh, of course they are, because if it is you're saying this is a convergent series, it adds up to cosine x, then that negative one is important. I think it's how you write it. In other words, that this one, because you wrote it as 2n, because what is the first thing you observe? That they are all evens. If they're all evens, then you know that this is 2 times 1, this is 2 times 2, this is 2 times 3, and this is 2 times 0. And this is where that comes. This therefore corresponds to n equals 0, this corresponds to n equals 1, n equals 2, and n equals 3, because n is your runner.
Got it.
Right? Amir, if you want to say for the power n plus, so is this you were answering, or I don't know, you put a question mark there, but the thing is correct. So I don't know if you were answering or this one. Oh, that is because remember, you have to understand this is n equals 0, Amir. So you want this to be positive. So, sorry, negative. So the only way this is going to be negative is when you have negative 1 to the 0 plus 1, which will be negative 1. This is n equals 1, so the only way this is going to be positive if you put n plus 1, and that is why it's negative 1 to the n plus 1. So I'm just going to erase some of the fluff there, and I'm going to say that is why this is, you just observed that this is an alternating series. And why do I keep harping on that? That is important. And important why? Because I told you, I have to show you why we are doing this. So why are we doing this? Questions about this one? Is everybody clear? Because we're going to use this. I'm going to build off on this one. So this is cosine x. You want to know the radius of convergence? You're going to do the ratio test, which I'm going to leave to you. But I can give it to you right now that your r will be infinity. Very important. So it works for all values of x. Oh, we did not know that. And maybe I'm going to change my mind a little bit here. I'm going to take one more example. Let's do this, and then I'll show you why we're doing it. So let's do this one. I'm looking at the time. Oh, we're okay. We're okay. And I want this at a equals 2. So if you want to participate today, remember today is the last day, you can unmute yourself and participate. So here we go. So when a equals 2, you know it's a Taylor series. You know this is the center. So you know what you're writing this as. You're writing ln x as summation n equals 0 to infinity cn x minus 2 to the n. So I'm going to make this ready. Well, what are those cn's? Oh, this is the nth derivative of ln x at 2 divided by n factorial. Now talk to me, people. Should I be making that table? Does that table help and does it make sense?
Yes and yes.
Great. Then let's do it. Then you know this is the prep. Once you have the prep, you start with the table. So it is n. And I'm just going to copy the nth derivative of ln x. This is this one evaluated at 2. And these are my cn's. And I'm going to fill them up as we go. So here we start. So n equals 0. So 2 came at ln x. Ln x at 2 will be ln 2. So you're saying, oh, this is ln 2 and it's timed by x minus 2 to the 0. I'm going to keep going. 1. What is the derivative of ln x?
1 over x.
Thank you, sir. Because I'm going to write it as x negative 1 for a reason, because I know the derivatives are coming next. So this is going to be what? Half then? So this is going to be half times 1 over 1 factorial x minus 2 to the 1. And do we agree with that? Are we okay with that?
Is that just a matter of notation on your part? Could we just as easily write it 1 over 2 times 1 factorial?
Yes. I just like to keep things separate, and you will see why. Because I like to think of them in terms of components when I start writing that notation. And that's why I keep them separate. So that was good.
Got it.
Okay, so let's keep going. So we are going to have what? 2. So that's the derivative of this one. So that's going to be negative 1x to the negative 2, right? And so if I do that, now that's going to be negative 1 over 2 squared. Now you will know what I'm saying, Russell. So this is negative 1 over 2 squared, 1 over 2 factorial, x minus 2 to the squared. And I'm going to keep going. Unless I see a question or somebody unmutes and asks one. So here we go. So this is negative 1 times negative 2, x to the negative 3. So this is negative 1 times negative 2, 1 over 2 cubed. I'm going to keep it that way. Negative 1 times negative 2, 1 over 2 cubed, 1 over 3 factorial, x minus 2 to the cube. Question to you. Should we be doing one more, or are we okay? One more from the table, or we all
Yeah.
right? One more? Okay. Let's do one more.
You might have lost me. I'm
the
just waiting.
Trick is not to complicate. So where did I lose you?
Well, I'm not sure yet. It just, you seemed to add the negative 1 and negative 2 in, and I think
Right,
you added it. Go
because
ahead.
that was the derivative of this one, Russell.
Right.
And so the negative 1 was already there. So I just took the derivative of this part, which is negative 2x cubed. Maybe I should write it this way. And maybe you can use colored pencils as well. So because this is just the derivative.
Right.
And that's why I kept things separate. So I didn't mess at all. Because you evaluated this one at 2, that gave you your 1 over 2 cubed.
Right.
And so I have the constants, this one, which I just copied. So I just copied this. And now multiply by 1 over 3 factorial. That is because of the thing you've got up there.
Yep.
And so I'm not messing about at all. I'm just writing everything separate. I'm just keeping separate. I'm not simplifying. I'm not doing anything. I'm just going this way. So let's do this one more time. So if it is 4th, then I'm going to say, oh, I'm going to just copy the negative 1, the negative 2. Now the derivative of this one, which will be negative 3x to the negative 4. So I'm just going to say this is negative 1, negative 2, negative 3, 1 over 2 to the 4th. And this is going to be negative 1, negative 2, negative 3, 1 over 2 to the 4th, times 1 over 4 factorial. I missed that board in the class, which should have been wonderful right now, because I could have written it all in a straight line. But you can. You have the paper and you have the power, therefore. So let's put it all together. So I'm just going to write it now. So I'm just saying, oh, what did I find till now? ln x seems to be ln2 plus half times 1 over 1 factorial x minus 2 plus, notice how I write that. I'm just going to say this. Can I write this as -1 so that you would see the pattern now? So it's -1, 1 over 2 squared, 1 over 2 factorial x minus 2 squared plus -1 times -2, 1 over 2 cubed, 1 over 3 factorial x minus 2 cubed plus -1, -2, -3, 1 over 2 to the 4th, 1 over 4 factorial x minus 2 to the 4th. At this point, you should be seeing some pattern. You don't have to like it, but you're seeing some pattern there for sure. So is everybody with me? Any questions? If you want me to pause, I'm ready to pause, but I want everybody written down. Today's the last day. I want to hear from Nera. Is Long here? I have no idea if he's here or not. Right, so Lucas, you're a bit ahead of us, but I'm going to show you how to think about this, okay? No, I just want to know that you're with me. And that's why I assigned you no new homework today. That's all I want you to do. Just look at the homework, and if you see I'm doing problems very similar to the homework, so you should be able to use this, your numbers might be different, and so on and so forth. So is everybody ready to see the pattern? Great. Nera has spoken, so we are all ready. So here we go. So let's do the first observation. This guy is different. This is odd one out. So there's no pattern. I can't fit this with this one. So I'm not even going to bother. So what do I see here? I go back to my table. Isn't this n equals 1? So I remind myself, oh, this term came from n equals 1. This is n equals 2. This is n equals 3. And this is n equals 4. So how am I going to write this in notation? So when I'm going to write this in notation, this one does not follow the pattern. So I'm just going to leave it alone. I'm going to say, okay, ln x is ln2 plus summation. Now you will know what I'm talking about. N goes from what to what now? Look at what we wrote here. So n
1
will
to
go
infinity.
it will be 1 to infinity because we know we started at 1. And now I'm just going to take care of the easiest parts. So these are the easiest parts for me. Oh, x minus 2 is just to the n. Agreed? Do not write, just observe. So what about this one? Oh, this is just n factorial. Okay. Now talk to me about the powers of 2. What about the powers of 2 here?
Isn't that 1 over 2 to the n?
Very good. So isn't it 2 to the n in the denominator then? Right? See, I'm combining now. I'm writing all of them together. And now I want to say, so Russell, if this is confusing you, let's do an intermediate step. And not just you, I just took your name, so don't be. So here we go. So this is what I'm saying. It is x minus 2 to the n. It is 1 over 2 to the n. It is 1 over n factorial, right?
Yep.
And you would see what I'm writing in the red up there is the same thing. So what is the one thing I have to take care of? Now what do I observe? Well, they're alternating. And that is why we estimated the alternating series, people. So it's an alternating series, isn't it? So for n equals 1, it seems to be positive. N equals 2, it is negative. N equals 3, it is positive. N equals 4, it is negative. So I'm going to take care of that one first. And because you like this, I'm going to come back here and do this. So this is negative 1 to the... What? If n equals 1 has to be positive, n equals 2 has to be negative, can we go with n plus 1 again on this one? There you go, William. That is that. What did you not take care of? Oh, you did not take care of this. You did not take care of this because now I'm writing those because this is, remember here, what did you take care of? You took care of the negatives. I'm talking about the numbers now. So when n was equal to 3, you had 1 times 2. When n equals 4, you had 1 times 2 times 3. So can I say here that this, and I'm talking about the numbers now, these numbers that I've circled in blue. Remember, the signs are already taken care of. I'm talking about these numbers that we did not take care of. And what do I notice? Oh, I notice that it is n minus 1 factorial. Can we do that? Yes, because when n equals 1, it is 0 factorial. When n equals 2, it is 1 factorial. We are perfectly fine. So I'm going to take this all up there. And I'm going to say, oh, this is negative 1 to the n plus 1. And this was n minus 1 factorial. And do we need to simplify? Yes, we can simplify this bit. And so here we go. Here is the final answer. So ln x is ln 2 plus summation 1 to infinity, negative 1 to the n plus 1, x minus 2 to the n. I'm going to do something, and you're going to tell me if that makes sense and why. This is it. So what did I do there?
Magic.
Better than that? You can do that one as well. So tell me, what did we do there? We just simplified the factorials, didn't we, Russell? So n minus 1 factorial. So I'm just going to say n factorial was n times n minus 1 factorial. You had n minus 1 factorial on the top, so we just cancel. You have to remember what the factorials are. Remember the Trump Tower and you're taking the elevator.
Got ya. Note to self, go over factorials with the tutor.
Okay. So, to find the radius of convergence, use the ratio test. Radius and interval of convergence, you use the ratio test. And remember, if they ask you for the interval, check the ends. I'm going to pause. So far, so good, people. Because now we have to do something else. No questions there? Okay. So here we go. So why are we doing this? And I promised you today that we would say, why do we write f of x as series? What is this all about? I'm going to remind you that this is an integration technique. Oh, thank you, Amir, but I seem to know that symbol. I just did not know when I got Zoom bombed and they said something like, somebody took my name and said, what? Lamal. Something like that. I have no idea. I don't even want to know. So this is an integration technique. And how is that? So here's an integral problem. So integral x cosine of x cubed dx. I want you to know that you cannot do this. This is an indefinite integral. You cannot do this until you write this as series because your USUB doesn't work. Your trig formulas don't work. Why? Because trig identities only work when you have a square. When you have cosine squared, sine squared, something like that, some powers. Otherwise, they don't work. So you're at a dead end, which means what? There we go. So, which means I'm just going to remind you to do this integral, to compute this integral, we can write cosine x as a series. How do we do that? We write it as Maclaurin series using that table. The question is, what do we get? If you look in your book, then these are the standard series, and sometimes they give it to you. So if we had more time, then we would have done more complex examples and they would have been given to you. But here it is. So cosine x is, I'm not going to go over the table again because I really want to get to the integral. So it is n equals 0 to infinity, -1 to the n, x to the 2n over 2n factorial. That is what cosine x is. So you wanted to integrate that. What does your theorem 2 say? That you can integrate term by term. So tell me now, if cosine x is this, what will be cosine of x cubed? I don't want the answer. I want to know, how are you thinking? How will you get this? If this is cosine x, what is cosine of x cubed? What should I do? And remember what we started the lecture with.
I'm guessing you're gonna just take the Maclaurin series.
And do what? Because the Maclaurin series for, there we go, Cecily. So Maclaurin series for cosine of x. So I am just going to replace this x by x cubed, both sides. We are done. So this is it. So n equals 0 to infinity, -1 to the n. I'm going to say x cubed to the 2n over 2n factorial. So that gives me cosine of x cubed is summation n equals 0 to infinity, -1 to the n, x to the 6n over 2n factorial. So far, so good. But remember, we wanted x. So what should I do? If I wanted x times cosine of x cubed, I want x times cosine of x cubed.
Just throw the x in front of
Very
the
good.
sum.
So multiply both sides by x. Okay, so I have x cosine of x cubed is summation n equals 0 to infinity, -1 to the n, x to the 6n plus 1 over 2n factorial. There we go, Lucas. Beautiful. Now what? You wanted to integrate that? Okay, integrate.
Wait, aren't we missing an x on the right-hand side?
Are we?
Aren't you supposed to multiply both sides by x?
I did, and when I multiplied this side by x, I got this.
Oh, I thought the x would go outside the summation.
It's not about outside or inside. I think what you have to imagine is that this, if you write out the series, which is what? -1 to the 0, x to the 0 over 0 factorial, plus -1 to the 1, x to the 6 over 2 factorial. If you imagine that, then when you bring in that x, as you said, what happens? This becomes times by x now. This becomes times by x to the 7. In other words, each exponent of x goes 1 up. That's what we did.
Ah.
So now we integrate both sides. And now I want you to understand that when you integrate sine x, you knew you were getting cosine x. When you integrated e to the x, you knew you were getting e to the x. When you integrated e to the 3x, you knew you were getting e to the 3x over 3. We don't know the integral of this. I don't know the integral of this. So you might name it after yourself and call it Nara function. So we are just going to say if I integrate both sides, then I get something called a Nara function, which is integral of x cosine x cubed dx is going to be, I don't know what to call it, so I'm just going to leave it like that. But as I said, it will be an error function. The constant of integral c plus, how do I integrate this one? Don't we integrate term by term? We've done this last time. So this will be what? Oh, n equals 0 to infinity. Remember, we are integrating, not differentiating. Negative 1 to the n. Amir, pay attention now. We can call another one Amir function. So this is going to be, I know you want to have fun. This is the last day, but I'm sorry. We lost 2 days in the class because when we transitioned to online, your final is coming from the department. So I do want to make an announcement. I'm looking at the clock because I wanted to talk about that final a little bit, and that's why I'm going this way. So this what happens? 6n plus 2, because the exponent goes 1 up. 2n factorial, 6n plus 2. So if you're wondering what this mumbo jumbo is, we just integrated this, and that is what this is. Right? The exponent goes 1 up, and you divide by the same thing. And that's it. So if you want to find the c, you really at the end, because this is an indefinite integral. So just like if I had asked you, what is integral of x dx? You would have said x squared over 2 plus c. So because this is an indefinite integral, you are just going to write it like that. But more importantly, I want to show you something else. So here we go. And this is my last example for the day, and it is going to tie up with everything that you have done before. I by P, you're going to go in circles, Lucas, because you're not going to come at this one. Because remember, when you do I by P, then probably you're going to do the derivative for this one. You're going to do the integral for this one. But then you are stuck again. What is the integral of cosine of x cubed? Okay, if not, you're going to switch. You're going to say, okay, I'm going to regard this as u, so I will get du. But remember what your du comes to. Oh, it will be what? Negative sine of x cubed times 3x squared, so it doesn't get any better. And so there are some functions, if you're an electrical engineer, there are some functions that can only be written as series. And as I said, if we had more time, I would have showed you, but it's called a Bessel function, which is only expressed as series. You cannot express it in any way else. So here is my last example. So I want you to find integrals 0 to, I'm just going to check if I copy it correctly. Of course I did not. So 0 to half x cubed tan inverse x dx, correct, to 4 decimal places. So what does it mean? That we want to estimate, there you go, William, that's correct. So we want to estimate this definite integral, which will be what? Some number, I don't know what. But we want to estimate the value of this, correct, to 4 decimal places. What does that mean? This means the actual minus your estimation should be less than or equal to 0.4 places after the decimal, you said. So 1, 2, 3, 4. I don't care what digit is there after. There could be some number after. And we start. And I picked this example for a reason. So I want all of you to stop writing. And let's talk it from the very beginning. So I'm going to say, I can write, start with this one. I can replace x by x squared. So I get 1 over 1 plus x squared. Now I integrate both sides. Which gives me tan inverse x, and this gives me x to the 2n plus 1 over 2n plus 1 factorial. Now call out. What did I made a mistake, and I did that very intentionally. So call it out. So what mistake did I make? Very good, Cecily. There we go. Yes, indeed. This is 1 minus x. So, in fact, I don't want to start with this series. And that's what I told you last time. I want to start with 1 plus x. But if I want to start with that, then this side should be negative 1 to the x. That is what that is. So what do I have to change here? Oh, this is negative 1. Oh, this is negative 1. And that is tan inverse x. Why is that important? Why is that thing that if I do not catch it, what happens? It doesn't become an alternating series. Now this is an alternating series. Why is that relevant? Because remember, this, you want to figure out how many terms should I add so that we can have these definite integral correct to so many decimal places. So let's start. So what do I want? X tan inverse x. Or what is that? X cubed tan inverse x. So I'm going to multiply both sides by x cubed. So I get summation n equals 0 to infinity, negative 1 to the n, x to the 2n plus 4, 2n plus 1 factorial, equals this x cubed tan inverse x. Again, why x to the 4? Because you know you're multiplying by x to the cube both sides. Now I'm going to integrate. Remember, this is a definite integral. So I'm going to say this is n equals 0 to infinity, negative 1 to the n, x to the 2n plus 5 over 2n plus 1 factorial, 2n plus 4 equals, and I'm going to write this is 0 to half because that was that integral. And this is integral 0 to half x cubed tan inverse x. So what is the idea then? First, I'm just going to write it out. So when x equals 0, all these terms are going to disappear. So here we go. And then I'm going to take questions if there are any. And this is n equals 0. This is n equals 1, which will be this is n equals 2. And so on and so forth. Maybe I should write one more. And this is n equals 3. So this will be half to 11 over, this is n equals 3, so 7 factorial, and 3 is 6 times 10. Oh, so it is 2n plus 5, you're right. So this should be 2n plus 5. So I just have to go one up. So this is going to be 5 then. This is 7, this is 9, and this is 11. Yes. So far, so good. So I'm just going to say this and stop writing, all of you. This is an alternating series. So if I know the error has to be less than or equal to 0.0004 decimals and some number, which I don't care, then what do? Maybe I start checking with this one, or maybe I start checking with this one. Remember, if this one is less than or equal to, you have 4 zeros after the decimal and some number, then you know you can just add these 3 terms and you are done. Then you have to check this one. If this one is less than or equal to 4 places after the decimal, then only adding the 2 terms will do. If you're wondering what happens to the 0, I'm just going to say this, I put the top in there, minus there should be the bottom, but x is all zeros, so bottom is all going to be 0. So I'm going to pause here a little bit. Questions? The factorial was not from integration, Cecily. The factorial was from how we came up with this one. So you're right. Why did I write the factorial? So it is not the factorials then. You are right, Cecily. So I'm just going to erase this so there are no factorials. Oh, that makes the calculation easy. Sorry, my bad. I'm looking at the clock. Yeah, so there are no factorials. No, William, we are not going to go with Cn with this one. And even if you go with Cn, you will notice that things cancel, just like the last time. So Cecily is right. I shouldn't have had a factorial there. I was rushing. So my bad, because we just integrated here. Sorry. So we just integrated here. Oh, jeez. So we just integrated here one more time. Yeah. So that was me. That was all me. So are we okay there? So I just want to say this thing to you. Before I take questions about any of the material, this is it. I'm not going to do anything further. And this is exactly where I wanted to stop. So Amir, if you remember in the alternating series test, you said that S minus Sn should be less than or equal to Bn plus 1. So if I found that n equals 3 is less than or equal to that, 4 places after the decimal, and n equals 2 is not, then that's it. I've reached it. So I'm just going to add this, this, and this. Whatever that number is, I guarantee it's correct to 4 places after the decimal. That means if you take the actual and subtract my approximation, you will get 4 places after the decimal. But you are right. If this is not, then what do? I write n equals 4 and see if this one is less than or equal to the size of the error. If it is, then I'm going to add n equals 0, 1, 2, and 3. Does that answer your question? Okay. So this is what I'm going to say to you. So first point I want to say is the final is coming from the department. I don't get to see it. I get to see it with you. So there are some sections that because we lost 2 days and we are a Monday, Wednesday, Friday class, other people who meet 2 days just maybe lost a day or something, but we were lost 2. So because we lost 2 days, I did not cover section 7.7, which is the trapezoidal Simpson's rule. I did not cover that. So what do I want you to do on the final? This will not happen, but if it happens and you see a question, skip it. Because when I put your grades in Canvas, I'm going to not count that question because I know we did not do it. Does that make sense? So you are going to skip it. And when I enter your grades in Canvas, I'm not going to count those questions. So even if the test is on WebAssign, and you will get maybe a 0 for that one. When you see the grades entered as your final grade, this question will not be counted. So don't worry about that. I can go in and remember, it's not your total on the WebAssign, it's your total in Canvas what says it. So do not worry, Canvas will go off and you can see your things on MySJS. So Canvas will go off for a while, which means I'm doing this sort of conversion here and there. So let me work in Canvas. And then I might, have Canvas up again so you can see your things, but your grades will be on MySJS. Yes, Bambi, that's I'm not going to count it. So if you want to, if you have seen this before, you know what Simpson's trapezoidal rules are, and you do it, I'm not going to cut your points. I'm just going to keep it then. So in other words, Bambi, if you know the material and the test adds up to 70 and you get 70 out of 70, I'm going to keep it. But for the others who have skipped the question, the test is going to be out of 69 and not out of 70, assuming that each question is 1 point, which your WebAssign does. Does that make sense? But be assured, that's the only thing that we did not do. There is another thing that we did not do, but as far as I know, nobody else has done it either because nobody got that, which is the binomial series, which would have, had we done binomial series, it would have been even more fun because now you can write even the sine inverse x as a series. So, but this we did not do at all. But there are some others that haven't done. So we also did not do force due to fluid pressure. So if you see that again, skip it. We have done work, but we have not done force. Some people have not done theorem of Pappus. Ilian, as I said before, I am going to see the final with you. I don't know what the final is. I'm just passing on information what the department gave to us. And it seems like, because of this pivot, everybody seems to have picked up some parts of it. They've done some parts, they've not done some parts. And so I'm just talking about my class, about our class, which is force, you're going to skip. If you are going to have 7.7, you are going to skip. Yeah, but I know there's one other instructor who did Pappus theorem, and we like that Pappus theorem. Lucas, I don't know. I agree with you that when we started it was that, but if it is on WebAssign and if I'm allowed to do these things and cater to my students, that what they don't know, I'm just not going to count them, then I don't see anything bad with it, anything wrong with it. And you've done so many homeworks on WebAssign, so you should be okay. Yeah, so I think we should be. I don't think, because I informed them that I haven't covered this one and I haven't covered this one. So hopefully the questions will not show up. But I was just trying to say, if they do show up, I wanted to give you a heads up that what will you do? You will just skip them because I haven't done force due to fluid pressure and we haven't done those. But don't go with the assumption that they will be there. Don't go with any sort of assumption. You should be able to answer every single question. I will be on there, so you can ask me via chat, and I can only reply to you if we have covered it or not. I cannot go beyond that. So I might be able to say, no, you should be able to do it. We've done it. So do not confuse with the material that we haven't done. So do not go with any kind of assumptions. But I still wanted you to not be thrown off when you see this word, trapezoid Simpsons, just say. That is what I was talking about, Aaron. It's just I don't know when to schedule it. And that's why I asked you for the days that, I don't know, do we want to schedule it on a Tuesday then? Because Wednesday, everybody seems to have finals. Tuesday seems to be a dead day, isn't it? Yes, Lucas. And if you look at the final instructions I gave you, I did say on there. Right, so Tuesday meaning tomorrow. So if you want to take a look at the homework today, and tomorrow maybe we can meet at noon. I can schedule a Zoom meeting at noon. I'll just put it in announcements. If you have any questions you want to join in, join in. If not, fine. No, Bhavni, because this is in weather sign. Please read go ahead and read the announcement there regarding the final. And same for you. Go ahead and read the thing there.
Thanks for everything, Professor. I'm going to take off.
Yes, sure, Russell. Oh, I just threw a noon in there, but what we have to, we want to meet at 2 p.m. then? Because my mornings are busy tomorrow. Okay, so let me just schedule a Zoom meeting for tomorrow. You will see it in your calendar at 2 p.m. Join in if you like, and or if not. Okay. So I'll let you go. If you want to stay back and ask questions,